have a sphere of radius r, yeah, centered at the origin, and it carries a charge density given by, so it's not a uniform charge density. The charge density changes, as you can see, with r and theta. K is constant. Yeah? Small r and theta are the spherical coordinates, and we need to find the approximate potential for points on the z-axis far from the sphere. So we're somewhere on the axis, on the z-axis, very far from the sphere, and we need to approximate the potential. Okay, so we spoke about the dipole approximation, potential approximation. Let's just assume, let's develop a more general result, of that similar scheme. So let's just say we have some volume distribution, whatever that is, yeah. And let's say we are at a point P that's very far away. Oh, this made it an ellipse. It doesn't have to be an ellipse. Whatever the shape is, potato-shaped body. Yeah? And let's say we are far away here at point P, and we want to approximate the potential there. So let's say that we place the coordinate system here. Yeah? So we can take a piece somewhere here, yeah, from that potato-shaped body, and the distance, we are inside the charge distribution. Let's say we have a uniform, or a non-uniform charge distribution, whatever that is, correct? And let's say that this is here is r prime. These are the prime coordinates, and from the origin to the point P, this will be an r, yeah. And of course these are vectors, of course. And from the so this is a d tau, yeah, here, this piece, or d tau prime, since this is inside the charge distribution, the prime coordinates. So this guy here will be what? The separation vector, yeah. Let's call this the separation vector. And of course this here, let's call it theta prime, the angle. Okay, well, what's the definition of the potential? Well, we know that V as a function of R is, for a charge distribution of any sort, is 1 over 4 pi epsilon integral 1 over the separation vector times rho, which is the charge distribution as a function of the prime coordinates d tau prime. Correct? Now, I'll take this triangle here that I've created, yeah, and I'll use the law of cosines to figure out what my separation vector is. So I know that my separation vector, according to the law of cosines, is, or squared, let's say, is r squared plus r prime squared minus 2 times the first times the second, 2r prime, cosine theta prime. Okay, so let me pull out an r squared out of this. I'll show you why in a second. 1 plus, what do we have left here? If I pull out an r, so I divide this by r squared because this didn't have any. And since they're both squared, I could do this. I could square the whole thing. And then I could do the same thing here. So this becomes r squared. There's an r, so I'm just going to have to divide by another r. And cosine theta prime. Right? And what I could do now is I could, let's see how we're going to do this. We could, why don't we call this guy here, uh, why don't we call this guy here, whatever the symbol is, or lambda. How about lambda? Let's go with lambda, something we know the name for. Okay, so if I call this lambda, then what's my separation vector becomes r squared, square root of that is r, square root 1 plus lambda. Yeah, and let's write out lambda more explicitly here. What's lambda? Because, you know, we're going to do an expansion, so let's call this lambda to be this guy. I'm going to pull out r prime over r, and what we have left is r prime over r, because the first one is squared, minus 2 cosine theta prime, correct? Minus 2 cosine theta prime, yeah, so this would be my lambda. Okay, now if we're far away from this charge distribution, right, notice that lambda depends on the ratio between r prime and r, but r is very large compared to r prime. So that means this lambda will hopefully be much less than 1. Okay, so whenever that happens, you know that you're looking at a binomial expansion. So my separation vector now becomes 1 over the separation vector, because that's what I have in the integral. So let me see what that is. So that's 1 over r, and then I have to divide by 1 over square root 1 plus lambda, yeah? Which is 1 over r 1 plus lambda to the minus half. And now I could do, since my lambda is a lot less than 1, I could do a binomial expansion on it, on my 1 over lambda separation vector. Yeah? So what would that be? If you remember, the binomial series goes something like this. 1 plus x, as long as x is a lot less than 1, to the k, is equal to 1 plus kx plus over 1 factorial plus 1 k times k minus 1 x squared over 2 factorial plus k minus 1 k minus 2. Remember your I mean, this came from expansion of a Maclaurin series, and it turns into a binomial expansion over 3 factorial x cubed, about 0.0, about x equals 0. And then, you know, I could keep on rolling. K minus 1, you get the idea. We don't have to go additional terms, etc. So this came from your calculus class, yeah? So I could apply this on that guy, and if I do that, let me go back to green. So I will get 1 over my separation vector will just be 1 over r. Okay, so in our case, k is minus half and x is lambda. And by the way, this works when x is a lot less than 1. Okay, otherwise it diverges. This is the interval of convergence for our series. Okay, so and we do have that in this case, because, you know, we just showed that lambda is a lot less than 1 because we're far from the charge distribution. So so my x is lambda, and my k is minus half. So this becomes 1 kx, which is minus half, and we said x is lambda, so lambda, and then we have minus half. So this is supposed to be plus minus half times minus half minus 1, which would be minus 3 over 2, right? And this is divided by what? By 1 over 2 factorial. And now this is lambda squared. And then the next term will be plus minus half minus 3 halves, because it's k minus 1, then k minus 2, so minus half minus 2 is minus 5 halves, over 3 factorial times lambda cube, and so on, etc. And so if I let me simplify this one step here. So this is 1 over r, 1 minus half lambda. What's this here? 8 plus 3 over 8 lambda squared. And the second guy will be what? 15 over, let's simplify the 3 with the 3, we still have a 2, so this is 2 to the 4th. 2 to the 4th is 16. There's 3 minuses, so that's a minus, so this is 16 here, the 3 cancelled out, and we get 5 lambda cube, etc. Well, k in our case is minus half, because it's 1 plus lambda to the minus half. Okay, so let me bring my lambda back now and plug it in for what it is. So remember, lambda was r, lambda was r prime over r, this right here. Okay, alrighty. So why don't we do that? So we get 1 minus 1/2, and lambda is r prime over r, if you remember, times r prime over r minus 2 cosine theta, plus the next term is 3 over 8, and now I have to square my terms, same thing, so r prime over r squared, and then we have r prime over r minus 2 cosine theta all squared. Let me go to the third term. It won't fit here, so I'll continue here. So this is, we got 5 over minus 5 over 16, and this is what, r prime over r cube into r prime over r yeah, all cube minus 2 cosine theta prime all cube. I should prime these because this is in the prime coordinates. Cube, etc., etc., etc. Okay, so this is my 1 over the separation vector. Okay, well, let's we have here r over r prime, r prime over r. This is a 1, this is a 2, this is a 3. Let's see, we can collect those. So let's collect the like powers of r prime over r. So if I do that, I will get, let me change the color here so it's less confusing, equals 1 over r, right? Well, if you multiply, you have, so r prime over r times cosine theta prime, that's this guy times this guy, correct? So this is, so the 1 stays there. We have minus minus, so this becomes plus, so r prime over r cosine theta prime. That's right? Yeah. Okay, and now next we have this times this. Yeah. So this will be probably easier to FOIL these before we could do that, because we're gonna get r squared times 4 of these, right? Yeah. You know what? It's probably easier to FOIL them. Let's FOIL them. So we have here. Let me just FOIL them. So 1, we get minus half r prime over r squared plus r prime over r cosine theta. That's the first guy. Okay, plus Now you're gonna get r prime over r squared, and you have an r prime over r squared, so that's 3 over 8 r prime over r to the 4, yeah, and then you have 3 over 8, we have 2 times the first times the second, so that's going to be a minus here, times 4, r prime over r, you have a cube term here now, because you know you have r prime over r prime over r, okay, times cosine theta prime. Let me see, did I take the 2 into consideration? Yeah, I did. And then let me continue here, so open this bracket, and then you have squared the second term, so you have 3 over 8, and you have a 4 because you're squaring it, and you have r prime over r squared cosine theta prime. You see? Yeah. Okay, done with that. Let's move on to the third term. So here we're going to get minus 15 over 16 r prime over r to the 4. Wait, no, more than 4. We have square, wait, and this here was cosine squared, not cosine, because you squared the cosine. Okay, so you're going to get cube the first, yeah? So if you cube the first times the outside, you're going to get to the 6. We're probably not going to need that term, but, you know, it just turned out to be that. And then if you cube the second, let me see if I need that. Yeah, let me cube the second. So, wait, how does the distribute? This is, so, this goes minus 3, so minus 3 times the first squared, which means r prime over r squared, and there's 3 outside, so that's r prime over r to the 5th, right? I'm expanding now, times the second, times the second, which is minus 2 cosine, so this becomes plus 2 cosine theta prime, and then of course there's the minus 5 over 16, so this goes back to become a minus 5 over 16. Okay, there we go. Now plus 3 times the first, some of these terms we're not going to need, but let's just expand up to the cube term. So 3 times the first, so let's write out the terms. So we have a minus 5 over 16, 3 times the first, which is r prime over r, but we have 3 outside, so this becomes to the 4, times the second square, so that's 4 cosine squared theta prime, minus the last square, minus, so this becomes plus 5 over 16, and then, I mean cube, 2 minus 2, so 2 cube will be, wait, I think I messed up with the signs here somewhere. Wait, let me do this. So this is minus 5 over 16, r prime, so the second cube, so that's 8 times r prime over r cube, yeah, times the second cube, so we already cubed that, and then we have cosine cube theta. Let me check my sign on the second term here. I think I messed up on the second term. Let me see. So this is 3 over 8, this is done. Minus 15 over 16, cube the first, yep, and then minus 3 minus 5 over over 16, 3 times the first square, which is r prime, okay, that's to the 5, times 2 cosine theta prime, yeah, and then plus, so plus minus, and here minus, oh wait, this becomes a plus here, right? And then the third one is minus minus, or plus minus, so it becomes, okay, now I think it's correct. Okay, so let's now group the, and then plus etc. Okay, so we expanded up to the cube. So what do we get here? We get, let's group them. So we have 1 over r. We have, let's see, where do we have cosine theta prime? Just once. Cosine theta prime just once shows up in, wait 1 second. This is when we square this, we got yeah, we got two. Yeah, okay. So what? Let's group them with the. So this is 1 plus. Okay, what multiplies r prime over r? Let's see. We only have a power 1. There's just one term, which is this. Okay. Is there anybody else with r over r prime? No, there's only one. So that's just cosine theta prime. So cosine theta prime. Okay, let's go to the square term. So this is r prime, because remember we're expanding according to this guy. So this is the square term. What do we have? Well, we have the minus half, right? We have this term here. And who else do we have with the square? We have right here, this guy simplifies with that guy, so it becomes 3 over 2 cosine squared. So I could pull the half out, or I could just say, yeah, I could pull the half out. So this is 3 cosine squared theta prime minus 1. Or I could, let me just put the whole thing over 2, it's better to keep it concise. Okay, and now we'll go to the third, and we'll stop on the third, yeah? Because from there, hopefully we'll catch the pattern. So plus r prime over r cubed. Let's see what multiplies the cube. So we have, change the color here. What multiplies the cube is, we have, okay, well, we have a term here. This is with a cube. Well, let's simplify this. So this is 2, right? So that's 5 over 2 minus 5 over 2 cosine cube. Wait, this was the last term in the expansion, correct? This is supposed, oh, there's a minus on the y cube, which turns this into a plus. Yeah, I messed up on the sign here. This is a plus because there's minus y cube, x minus y all cube. The last one is minus, and there's minus on the 5 over 16, so it becomes a plus. So here we have a 5 over 2 cosine cube theta. Okay, what else? Do we have another term? We should, let me see, we should get another one, yeah? For the cube. Because there was a cube, oh yeah, it's right here. So this is this guy. Well, what's that? 2, let's change the color. If we simplify this, this is a 2. So what's that? Minus 3 halves cosine theta prime. So minus 3 halves. So we'll just put the whole thing over 2. So minus 3 cosine theta prime all over 2. Exactly. This is the coefficients are turned out to be Legendre polynomials. It's actually a remarkable result. So so that's 1 over the separation vector, yeah, and since they turned out to be the coefficients of Legendre polynomials, then at this point we can just do that, yeah, because you know, we can follow the Legendre polynomials general series term, which is 1 over the separation vector will just equal 1 over r, the summation from n equals 0. Notice r prime over r is, here it's 1, here it's 2, here it's 3. So this is just r prime over r to the n. So if n is 1, if n is 0, you get 1. Hopefully now we're going to fix it to get 1. If n is 1, you get the r prime over r squared, etc., etc. And now those are the Legendre polynomials coefficients, which can be defined by Pn cosine theta prime. When n is 0, you get 1. When n is 1, you get cosine theta prime. When n is 2, we've done this before in the math class, and you could look up the Legendre polynomials and test it. When n is 2, you get the second Legendre polynomial, which is 3 cosine squared, 3 halves cosine squared minus 1, and so on. Okay, and so now I can take this and plug it into my potential formula, which I started with at the very beginning, right here, the integral, the top one. And if I do that, what do I get? I get the general result for V. So VR turns out to be 1 over 4 pi epsilon, the summation from n equals 0 to infinity, yeah? Now notice that I can pull this r inside the summation here. So it's 1 over the separation vector, so it turns out 1 over r to the n plus 1, because I have r to the n and another r. And then remember, the integration is with respect to the prime coordinates, so I can take r prime inside the integral. So this is r prime to the n, yeah? And then I have the Legendre polynomials, cosine theta prime. And then I have the volume charge density, rho r prime has to be inside because it's a function of the prime coordinates d tau prime. And if I integrate this over a volume, this is a volume integral, you know, I figure out what my terms are. So yeah, this is a very general result. It does get you all the terms here. So for example, if let's expand this for a few terms to see how it works. So what if n is 0? If n is 0, what do we get? Well, let's keep 1 over 4 pi epsilon out here. Okay, and so we get, if n is 0, we get 1 over r, right? P0 cosine theta prime, that's 1, so we get rho r prime d tau. Plus, now if n is 1, we get 1 over r squared integral r prime. The first Legendre polynomial is cosine theta prime, yeah, with respect to the angle, rho r prime d tau prime. This is supposed to be prime. Okay, and then plus let's make this longer. Plus, what if n is 2? I get 1 over r cubed integral r prime squared. And then what's the second legendary polynomial? We said half 3 cosine squared theta prime minus 1 over 2 rho r prime d tau prime, etc., etc. Right? If you expand this result, this is the multipole expansion of V in powers of 1 over r. Right? This term here, let's look at these terms individually to see what they're telling us. What's this? This is the first term is going as 1 over r, yeah? So this first term here is the monopole term, the monopole contribution to the expansion. So it's inversely proportional to r. If you look at the second one, this is inversely proportional to r squared, and so this is the dipole one. And if you look at the third goes as 1 over r cubed. So which one is this? This is the quadrupole. The whole thing. If we just give it a different color.
Alright, so it's the dipoles are squared, the quadrupoles are cubed, and
yeah.
Okay.
This is the quadrupole, and then I can keep on expanding to the fourth octupole. Yeah, the fourth one will be the octupole, and etc., etc. Now, so now I did the expansion, correct? Now I'll get back to the question. We have, remember, this was just getting to the general form of V. Now I have to apply this to my coordinate. Yeah, we have to plug it into this question. So, yeah, let's do that. From here on, it should be straightforward. Because, well, let's look at the monopole term for this question. I showed you at the very end what the monopole term is.
Did it say that the net charge was 0?
No, it didn't.
No, it didn't. It's a very general.
Yeah, so if I apply this to our question, then let's do it here. So what's our monopole term?
It's,
so V mono will be 1 over r, 1 over 4 pi epsilon, 1 over r, rho r prime d tau prime. And we have d tau. Yeah, I mean we have rho, so we can just plug it in.
Yeah.
So we get, let's see what this is. 1 4 pi epsilon 1 over r. Yeah, and rho is I can pull out the constants. K r, right? Kr, and then the rest has to stay inside. So we have integral of, let's see, r minus 2r. So we pulled out the kr and we have over r squared. So we can see 1 over r squared, right? Sine theta. And what's d tau? This is a volume integral. So, you know, well, it's, as you remember, it's r squared sine theta, yeah, dr d theta d phi. These are the volume integral spherical coordinates, with r going from 0 to r. Theta is going from 0 to pi, and d phi is going from 0 to pi. Okay? Now we can quickly simplify the d phi term. That's just going to get you a 2 pi. But let's see what, let's do the r integral separately just to see what we get, because I have a feeling here. Let me see. So the 1 over r squared. Oh yeah, we could cancel this with this. Okay, so good. So we get here kr over 4 pi epsilon r, and then we get so we gotta get 2 pi from d phi. So this guy is already taken care of. We're gonna get r minus 2r. That's integrated on dr. There's no theta dependence on this, and then we're gonna get sine squared theta d theta from 0 to pi, and this is and this is 0 to r. Let's see what's this guy. This guy is r minus r squared from 0 to r. Yeah, this is gonna be 0, because you're gonna get r squared minus r squared, and 0 makes them 0, so the whole thing goes to 0. So it doesn't matter what the rest are. Then v monopole turned out to be 0.
That means there must be a.
Well, let's go to the dipole term, because we already derived the result for all of them.
No, but the monopole being 0 must mean that there's no net charge, right?
The monopole term being 0, that is correct. That means the total charge is 0.
You mean the net charge?
Yes. Yes, because you know that term is in the.
0, because total charge can't be 0 because it's
Let's check the dipole term. So the dipole term is the second guy here. So that's v dipole is 1 over r squared integral, volume integral. What was it? I could have just copied and pasted that. Let me whatever. R prime cosine theta prime. So we have here r prime cosine theta prime. Was it rho r prime? Rho r prime. So what's rho? Rho is what we have. Rho is what we have. It's k r squared, kr over r squared, r minus 2r sine theta d tau prime. Right, and then I have outside 1 over 4 pi epsilon. Isn't it? Yeah, and 1 over r squared, we took care of that. Okay, so let's try to simplify this guy a bit. So, right? So we get v for the dipole, 1 over 4 pi epsilon, 1 over, let's bring kr out, so kr over r squared, right? Now, let's, so here we have left with r prime, so this is the integral of r prime cosine theta prime, yeah, r prime cosine theta prime. This is what we're integrating in. This is kr is outside, so this is r minus 2r over r squared, and d tau prime will be r squared, right? R r squared, r squared goes away, r squared sine theta, yeah, and then what else, dr d theta d. Okay, so again, triple integral, 1, 2, 3, dr is 0 to r, 0 to pi and theta, and 0 to 2 pi and phi. Okay, what do we have here? Well, I could, wait, did I forget a, did I forget a sine term? Oh yeah, there's a sine theta involved. I forgot a sine theta. No, I didn't forget it on the first one. Okay, good. Just forgot it on the second one. So this becomes a sine squared here, right? Okay, now wait, looks like the angle integral here will be 0, yeah? Let's test it. So if we integrate from 0 to pi, let's do it in components. It's better, easier. So 0 to pi, we are integrating sine squared cosine d theta. Well, this is u du, sine is u, du is cosine theta d theta. So this turns out to be u squared du, right? You know what I did, yeah? I just called sine theta u. If sine theta is u, du is cosine theta d theta. And then, wait, let's change the bounds according to that. So if theta is 0, yeah, it's going to be 0 because this turns out to be u cubed, u cubed over u over 3. Right? So this will be 1/3 sine cube theta from 0 to pi. But sine 0 is 0 and sine pi is 0. So this guy is 0. So this whole integral goes to 0. So that means the dipole term is also 0 on this question, on this charge distribution. Okay, so that means we're going to have to go to the quadrupole term. Yeah? Let's see what the quadrupole term looks like. Yeah, this turned out to be a longer question than I expected. Well, don't forget that I showed you in general the derivation for the multipole expansion. For the, yeah. So, so if we go to the third guy, yeah, the quadrupole term. Okay, let's do the quadrupole term. Okay, what was the term for that? We derived the result up there. Let me copy it and paste it down here. This was this guy here, yeah? So let me copy it and paste it. It's up to here. Yeah? Copy. And then I could just bring it down here. Okay, let me put it here. Okay, so and before it there's so this is the V for the dipole, quadrupole, and before it there's 1 over 4 pi epsilon. Okay, and this is a volume integral. Okay, let's plug in there the rho. So V for the quadrupole will be 1 over 4 pi epsilon 1 over r cubed. Yeah. Bring out the what was rho? Rho was k. So I'm gonna start simplifying right away. Okay, and then we have r minus 2r over r squared, and we have an r squared here, and what else? We have an r squared. We have this. So I'm plugging in for rho now. I still have from rho sine theta. Okay, and then I'm gonna put down the Legendre polynomial term. So this is 3 cosine square theta minus 1 over 2, and we set, and then there's the volume integral here in d tau prime. Okay, now we already know that the integral of d phi is 2 pi, from 0 to 2 pi. So let's just start simplifying, because this looks like a long integral. So this becomes 1 over 4 pi epsilon 1 over r cubed kr. Let's bring the half out. Yeah. I could just make these go away. No. And I have r minus 2r. So let's bring out the half. So if I bring out the half, I'm just going to put it here. So this 2 is this 2. And we have r minus 2r sine. And there's another sine from d tau prime. So this is sine squared. And there's an r squared. I'm going to put it here. And then what else? We have 3 cosine squared theta minus 1 dr. There's a 2 pi from d phi. I'm just going to put it here. And then d theta. So now I turned it into a double integral. So this is 0 to r and 0 to pi. Okay. Well, the second one doesn't have an r, so these are independent integrals. Let's do the r integral separately. So let's do the r integral separately. So this is 0 to r squared r minus 2r cubed dr. So what's this? This is r cube r over 3 minus 2 over 4 r4. Oh, stop writing. Too much pressure on the pad. Let me try to open it. Okay, minus 2 over 4 r4 from 0 to r. So what's this? Plug in big R. Small 0 will just make them 0. So we're going to get r4, because r4 over 3, right? Minus 1 half r4 1 half. So what's that? Minus 1/6. So we get minus 1/6 r4 on this term. Yeah, and then the angle integral, that shouldn't be too bad. The angle integral is, so now the theta integral. So we are integrating from 0 to pi. Yeah. We have 3 cosine squared theta minus 1 times sine squared d theta. Those are both even, yeah? Well, you could split them up. The best way to do this is replace cosine squared with sine squared, yeah? So this becomes 0 to pi 3, let's see, or sine squared with cosine squared, whatever. Probably easier to do cosine squared because there's a 1 there. So cosine squared is 1 minus sine squared. So this becomes 3 minus 3 sine squared minus 1, which would just make this 2. Let's just remove the 3 and the 1 and make this a 2. And then we have sine squared d theta. So what does this become? This becomes, let's see, if you FOIL this, so this is 0 to pi 2 sine squared theta minus 3 sine to the 4 theta d theta. Yeah? 0 to pi. Now, okay, these are easy integrals if you know how to do them. You know, basic calc too. Sine squared is 1/2 1 minus cosine 2 theta d theta, and I can cross this 2, this 2, this is 0 to pi. The sine to the 4th, first you need to turn it into sine squared squared. So this becomes 3 over 2, this is a minus here, and then sine squared is the same thing, 1/2, but this is squared, 1 minus cosine 2 theta squared, because it's sine squared, d theta, from 0 to pi. Okay, so this becomes, if we integrate the first one, this is theta minus sine 2 theta over 2, chain rule, from 0 to pi. Here, we're going to have to FOIL it. So this is going to become 3 over 8, is 2 squared, yeah? And then we're going to get 1 minus 2 cosine 2 theta, which both these are simple, but then we're going to get again a cosine squared, 2 theta. Okay, so we're going to go back and apply reduce this guy to a power 1, just like we did up there. And so let's see what we get. So here we get pi minus sine 2 pi over 2. The 0 will make them 0 because sine 0 is 0, and this is 0. So minus 3 over 8, 0 to pi. This becomes 1 minus 2 cosine 2 theta. Cosine squared we said is 1/2 1 plus, oops, wait, sine, yeah, this was sine squared. Okay, never mind. So cosine squared is 1, it's the same thing as sine squared except it's addition instead of subtraction. So 1 plus cosine, double the angle. Now the angle is 2 theta, so this becomes 4 theta. D theta. Okay, so now we're down here, we're down to a pi on the first one, minus 3 over 8, right? Now let's, when you FOIL the half here, you get a half and there's a 1, so this is 3 over 2, minus 2 cosine 2 theta, plus 1/2 cosine 4 theta, d theta, 0 to pi. Okay, now this became a basic integral again, 3 over 8, what's this? Let's open gate here, 3 over 2 theta, minus 2 sine 2 theta over 2, we can cross these out, and then cosine is minus sine, so this becomes 1 over 2 sine 4 theta over 2 over 4, sorry, chain rule, and this is from 0 to pi again, so we're going to get pi minus 3 over 8, yeah, and then here we get, so now evaluate, so this becomes 3 pi over 2 minus sine 2 pi is 0 and sine 4 pi is 0, and 0 will make them 0, so only one term survives. So what do we get here? pi minus 9 pi over 16. 9 pi over 16, so what's the 16 minus 9 is 7 pi. Wait, minus 9 pi is 16, 16 minus 9 is 7. 7 pi over 16. Let me see the calculator. Let me confirm this answer on the calculator. What was the answer? Wasn't an integral. This was 0. Yeah, this 2 is not supposed to be there because I already squared the half. Because it's half. Okay, squared. Okay, yeah. So I don't need that 2. So this became 4 here, right? And then if this becomes 4, now how does this change things? So this is 4. I think this is the only thing. And then minus 3 over 4. Then we have 3 over 2. Let me see if this changes it. So 3 over 4. 3 over 4. Which becomes, this becomes an 8. Yeah, that's what the calculator gave. Minus pi, because this is 8 pi minus 9 pi over 8. So we get minus pi over 8. Okay, bingo. So now put them together. So the integral now becomes, we have, let me copy this here. So the integral becomes, yeah. Okay, so let's paste it here. So after the KR comes the result, okay? Because I integrated all that, so we get KR times, we got from the R integral, what was it? Minus 1 over 6 R to the 4. So minus 1 over 6 R to the 4. This was the R integral. And the theta integral was minus pi over 8. No? So, right? So we get V quadruple to equal, let's see, we have R to the 4 and R, what's that? R to the 5. And then pi goes away with pi. The 2 can simplify this to 4 minus minus plus. So this becomes K pi, right? K pi, we have 1 over 4 pi epsilon. We have R to the 5. We have R to the 5. What else? We have 6 times 4 is 24. So we have another 24 here. Oh, and then we have the 2. So that's a 48. And we have an R cubed. Right? So this would be the potential for the quadrupole. It didn't turn out to be 0.
How come there's no, how come pi's within the pi cancel?
1 pi cancels, but there's 2 pi's.
Yeah.
There's one from the phi integral and one from the theta integral.
There's pi here and pi here. You left the.
Oh, yeah, right. I left a pi. No, yeah, this pi cancels. There's no pi here. So I meant to put the square and cancel it, but it's okay. Let's just cancel it. Now, of course, as you go far away, right, on the z-axis, r becomes approximately z, right? Because I mean, on the z-axis, you know, cosine theta becomes very small. It's just 1. Cosine 0 is 1. So then you can put that there, and for your final result, you can get as a function of z, yeah, pi k r to the 5 over that. Click on us on the final result. Yeah, 4 pi over pi k r over 4 times 48, whatever that is, epsilon, yeah, and this is our fifth, and then what's 1 over z cubed? There you go. So this is approximating the potential did I forget the 48? No, I have the 48. No? And this is the okay, so this guy here is the potential of this charge distribution. I hope this question gives you a very good idea of what multipole expansion in this section is all about.